Hello everyone, welcome back to Energy Conversion System 1. Previously, we already talked about centrifugal pumps, and from this point we will proceed with another type of pump that is called as an axial pump. In this video, we will talk about three main subtopics, that is the axial pump constructions, and then we will continue on discussing about the velocity triangle of axial pump, and then we will have a look also on the characteristic curve of an axial pump. To begin these sections of the course, we need to be able to differentiate between a centrifugal pump and an axial pump. So basically, when we talk about centrifugal pump, we will deal with a pump that will be used to work against a high number of head. So normally a centrifugal pump is being used to move fluid from a lower place to a higher place. However, in centrifugal pump, normally the flow rate is relatively small and head is relatively high. On the other hand, the axial pump normally works the other way around. So we normally use axial pump when we need to have a higher flow rate, and it only works on a small amount of head that it can covers. Normally an axial pump can work in a range of up to 20 meter in terms of head, and normally an axial pump we can find it in some engineering applications such as in shipyard construction, and also it can be found in and for waste water treatment. So normally in a factory or in chemical processes, they have this wastewater from the process or from work that need to be dealt with, and it has to be moved from one point to another point, but it doesn't require a high amount of head, so the selections will be for axial pump to deal with the wastewater. On the other hand, for example, when we have flood and this high water has to be moved somewhere else in a short time, therefore we need a high flow rate. So flood mitigations also normally use axial type of pump, and also in other irrigation system, normally farmers use it also to control the water going into the farm, and so on and so on. And yeah, not only in this area, also in power plant normally we also found axial pump being operated. For example, when they need to move the water into the boiler to generate the steam, they also use axial pump in some cases. Yeah, so the key is when we need a high amount of flow rate but only a small amount of head, we can choose axial pump. So what is axial pump actually, and how does it look like? So we will see it on the next slide. Now let's talk about the constructions of an axial pump system. So system means that it's not only the impeller itself, but also what makes the pump rotate, what makes the pump rotating, and how is the fluid being drawn from the source. Let's say that we have a pond of water here. So yeah, water pond, and we need to move this water somewhere else. So don't get confused by the constructions because it looks like it will bend somewhere and it will the fluid will not move in axial directions. But yeah, we will get into that after this. So to move the impeller, we need an electric motor, of course, to drive the shaft, and the shaft is connected to the impeller, and we call it rotor blade. And also we have stator plate that remain stationary and stick to the wall of let's say the pipe. So this is actually the casing of the pump, or it can be a pipeline. And we have the rotor blade, and the fluids comes in from the suction side or the inlet. And normally the axial pump has a impeller that looks like propeller of a ship's for any boat, then yeah, or fan for example. And it has a number of blades that normally consist from 2 up to 8, so there will be minimum 2 of these or maximum 8 of them. And the ratio between the tip diameter and the hub also, sorry, this is the ratio between the tip and hub. So the diameter ratio will lies between 0.3 up to 0.6, and the fluids will be flown, and it's getting the rotational speed from the impeller here, or the propeller, so to say. So the impeller, it's in a propeller shape. So you can have a look, try to Google it, or have a look on the textbook, and you can have a look on, get the idea of how the rotor blade of an axial pump looks like. On the other hand, what we should take note from an axial pump, that the flow area, the cross sections area of the flow, so this area will remain constant. So as the consequence, if in centrifugal pump we have the tangential component, or CR, at the outlet, or at the outlet of the impeller, will be different than the CR, or the tangential component, at the inlet of the impeller. However, this is due to the change in flow area in a centrifugal pump. However, in an axial pump, the tangential component CR2 is equal to CR1, since the flow area remains constant along the pump system. So therefore CR2 equal to CR1, or we can simply call it as axial velocity, or CA. This is actually due to the area that doesn't change. That means that the radius, or the diameter between inlet and after leaving the impeller, will remain constant. So therefore, as a consequence, the speed of the impeller, or the rotational speed of the impeller, or U, that is a function of omega and R, is also constant. So U1 will be equal to U2 as a consequence of R1 equal to R2. And now let's have a look at the velocity triangle of an axial pump. So up here we have the conditions at the inlet, down here we have the conditions of the outlet. So as we know that, let's assume that the pump has a straight configurations like this, and we have the impeller that gives the power to the fluid and increase the key. This is stationed here, and then as we've discussed before, since the ratio at the inlet and the outlet can't remain the same, we will have an identical omega and u. Therefore, the radial component or the tangential component is also constant, CR2 equal to CR1 equal to CR2, and it's being called as the axial velocity component, which is here, and it remains constant from the inlet and the outlet. And the amount of u is also identical. And then let's analyze the velocity triangle in order for us to get the Euler head, or the head being developed by the pump. So as we know, the basic equations look like this, that E is equal to U multiple with Cx2 minus Cx1 divided by gravity. This is the basic form of the equations, if you remember. And assuming that there is no swirl at the inlet, or Cx1 equal to 0, we can delete this. And then from the velocity triangle, we can get the idea that the cotangent of beta 2, or the blade angle at the outlet side, is equal to u minus cx2, because we need wx2 here, divided by ca. And therefore, by manipulating these equations, we can get the cx2 out on the left side, and then it will be equal to u minus axial velocity component multiplied with the cotangent of beta 2. And we put it back to the Euler head equations, and then replace cx2 with this to get this final form of equations. So when we compare back to the centrifugal pump, where we will have a difference u, or blade velocity, between inlet and outlet due to the increase in the radius of the impeller. But in axial pump, as the radius of the impeller constant between inlet and outlet, the difference is only, if we look from the front, and this is the blade of the impeller that looks like a fan, only the tip radius and hub radius that change. So there's, we can get the mass flow rate flowing in an axial pump. So it is a function of density, axial velocity, P, and multiply with the difference between the tip radius to the power of 2 minus the hub ratio to the power of radius to the power of 2. Now let's have a look on the typical head power flow rate curve of an axial pump. So this is the red line represent the head, and the blue line represent the power consumptions of the pump, and it's being plotted against the flow rate in cubic meter per hour. And these different lines in blue and red is based on the pitch of the blade. So pitch is actually when the blades look like this. So it's the angle represented how the blade is being twisted and so on. So the angle is represent the twist of the impeller, or the blade of impeller. So it's also the common terms in aerodynamics when we talk about airfoil and so on. So this is a common words in fluid dynamics actually. So yeah, so 10 degrees, 15 degrees, 20 degrees, and 25 is the pitch angle. And it's as we can see, as the flow increase, we will have less and less head can be developed by pump. And also we can see here the pump power consumption is at its highest point when the flow rate is low. Let's assume that the omega is remain constant, and then we have to flow the fluid at 1000 cubic meter per hour. And then as to control the flow rate, we normally control it through a valve. So let's say that the valve is only being open in a small opening. Therefore, the power consumption is getting high. This is actually we can attribute to the head energy equations, where it is a function of E equal to U multiplied with U minus CA to the cotangent of beta 2 at the outlet and divided by gravity. So as the flow rate increase, so this part will also increase, right? So therefore the energy will be decreased mathematically. So therefore we see here the energy consumption is getting lower when the flow is increasing. So mathematically that's how we are going to explain it.